All right, looking at section 9.2 here, working off of the previous one where we looked at counting methods. Now we're going to go into probability, which is more like calculating the chances that something will occur. Still looking at it from an insurance slant, but we're going to just start with the math of it. So it starts you off on page 10 with this note that there's going to be a Desmos. It's actually amplify, but if we're going to do an amplify activity soon, that's coming up toward the end of class today. So right now, let's look at these couple of probability problems. Let's make a note here what the definition of probability is. It's going to be a fraction, and you're going to write the desired outcome in your numerator and the total outcomes in the denominator. Okay, so we're going to put what we want on top and what the total possibilities would be on the bottom. So probability of drawing a highlighter from this bag. We have pens, we have pencils, we have highlighters, we have markers. That's 4 different writing utensils. So the total outcomes is 4. Could draw any one of 4 writing utensils. And it does say equal numbers, so I know that that's 4 different possibilities, equally weighted. Only one of them is a highlighter. So that's one way to write it. I could write it as a decimal, or I could write it as a percent. Any of those are valid. The marker, same thing. I've got 1 out of the 4 writing utensils. So also 0.25 or 25%. Highlighter or marker means I need to get either or, so I can write the probability of the first one plus the probability of the second one, and that sum gives me the possibility of getting one or the other. So that's 2 utensils out of 4, which would be 0.5 or 50%. All right, so item 2, you have a bowl of gummy bears, 5 blue, 15 red, 15 green, 15 yellow. So unlike the previous problem, I cannot use a denominator of 4 this time, even though I have 4 colors, because they are not equally weighted. So I can't split it into 4 equal parts. What I need to do instead is establish that there are 50 total gummy bears, and let that be my denominator. So probability of getting a blue is over 50. When I look for the blue, it says there are 5 of them, so 5 over 50. Fractions need to be reduced, so that's going to become 1/10. You can write it as a decimal, or you can write it as a percent. All right, so if we don't have equally weighted options, we do need to establish a new denominator to show that. Probability that we do not get a blue gummy bear. So this apostrophe that's here after the word blue, that is telling us that we are trying to figure out the chances of that thing not happening, which means any of the other things. So the way we can do that is start off with a whole and subtract the fraction of the time where the blue does happen. If we do that, we're going to get 9/10, which is 90%. Or we could have gone with the percent version and done 100% minus 10% and got 90% that way. But generally speaking, what we're saying here is that the probability of an event not happening, remember the apostrophe means not happening, we can take 1 minus the probability of that event happening. And that's a way to get it faster than doing a direct calculation. So let's keep that in mind whenever we come up with one that's asking for a complement with an E, meaning goes with but isn't exact. Okay, page 11. Fair-sided six-sided die, fair six-sided die. So we have 6 possibilities of this coming up. Right? We're going to roll a 1. That's 1 out of 6. That would satisfy getting a 1. The 5 would be 1 out of 6 as well. There's 1 5 on the die. If we add these together, we get 2/6, which is 1/3. So 1/3 of the time, we will roll a 1 or a 5. Right? Now we're saying the probability of not rolling a 1 or a 5. And again, it's noted with an apostrophe. So what we can do is 1 minus the probability of getting a 1 or a 5. Well, we just calculated that. It's 1/3. So we have 1 minus 1/3, or 2/3. All right, it's just a faster way to do a direct calculation when we want the complement. Okay, so moving on to the next part. There is a video that's going to go with this, so you can pause here and preview these questions so you know what you're looking for. And I am going to roll the first half of this video. It's going to come up as 12 minutes. We're not going to do the whole 12 minutes. All right. So here we go.
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. If you've ever seen a face in an onion or a grilled cheese or any other inanimate object, you've experienced pareidolia, which is a product of our brains that causes us to see the pattern of a face in non-face objects. This happens because our brains are so good at seeing patterns that they sometimes see them when they're not really there, like a face in this bell pepper. And faces aren't the only patterns we see. Our brains recognize patterns in everything, especially in sequences of events, like the kind we're going to talk about today as we start talking about probability. All right, first let's just establish a more specific definition of what probability is, because the way we use the word in everyday life can be different from how we use it in statistics. Statisticians talk about two types of probability, empirical and theoretical. Empirical probability is something we observe in actual data, like the ratio of girls in each individual family. It has some uncertainty because, like the samples in experiments, it's just a small amount of the data that's available. Empirical probability, like sample statistics, give us a glimpse at the true theoretical probability, but they won't always be equal to it because of the uncertainty and randomness of any sample. The theoretical.
So she's saying if you do an experiment, if you collect data, it's not necessarily going to be the same as a mathematical probability because you've collected a smaller sample size than what you could possibly do in a large version.
Probability, on the other hand, is more of an ideal or truth out there that we can't directly see. Just like we use samples of data to guess what the true mean or standard deviation of the population is, we can use a sample of data to guess what the true probability of an event is. Say you play a slot machine over and over and over and over and over and over. You'll be able to guess the probability of winning the jackpot by counting the number of times you win and dividing it by the number of times you played. If you play 100 times and win 6 times, you can be pretty sure that the probability of getting a jackpot is around 6 out of 100, or 6%. Now, this isn't to say that you can rule out the true probability is 5% or even 10%, but you're relatively sure that it's close to 6% and not, say, 99%. So the empirical probability can be a good estimation of the theoretical one, even if it's not exact. So far, we've been talking about the probability of just one event, but often there may be 2 or more events that we want to consider. Like, what if you want to know the probability of picking a purple or a red Skittle from a bag? The proportion of each color in a bag of Skittles is roughly equal, 20% for each of the 5 colors. So let's say you randomly select a Skittle without looking. For this, we need the addition rule of probability. Since a Skittle can't be 2 different colors at once, the color possibilities are mutually exclusive. That means a probability.
I think a Skittle could be two different colors at once if it melted in the bag, but that's not really relevant to this. We'll keep going.
The probability of a Skittle being red and purple at the same time is 0. So we can use the simplified addition rule, which says that the probability of getting a red or purple Skittle is the sum of the probability of getting a red and the probability of getting a purple. Since we're gonna...
So that addition that we were talking about before, when the word or appears, you're only able to actually add probabilities like that if there is no way that both of those things could happen at the same time. So when we're rolling the die, we can get a 1, we can get a 5, but you can't roll a die and get both a 1 and a 5 on the same cube. So that's why that addition was allowed. And she's saying here the same thing, that you can use the addition rule if it's mutually exclusive.
I'm going to be talking a lot about probability in the next few episodes. I'm going to introduce a little notation. Instead of writing out the probability of red, we can use the notation P of red. The probability of getting a red or purple would be written P of red or purple. So far, we know what the probability of red or purple is. It's P of red plus P of purple, or 0.2 plus 0.2. That equals 0.4, or 40%. I like all Skittles, so the probability I will get a Skittle I like is 0.2 plus 0.2 plus 0.2 plus 0.2 plus 0.2. That's 100%. Good odds. Red and purple Skittles are mutually exclusive, but not all the events we're interested in are. For example, if you roll a die and flip a coin, the probability of getting tails is not mutually exclusive of rolling a 6, since you can both roll a 6 and flip tails in the same turn. Since P of tails or 6 is not equal to 0, these two events are not mutually exclusive, and we'll need to adjust our addition rule accordingly. The full version of the addition rule states that P of tails or 6 equals P of tails plus P of 6 minus P of tails and 6.
See, if you forget to subtract out when they both happen, then you're essentially double counting. So all the times that you flip tails, one of those times is also going to have a 6. So if you don't subtract it out, you're double counting that one instance where you do get both.
When two things are mutually exclusive, the probability that they happen together is 0, so we ignored it. But now the probability of both these things happening is not 0, so we need to calculate it. You can see here there are 12 possible outcomes when flipping a coin and rolling a die. There are 6 outcomes with tails and 2 outcomes with a 6. If we add all of those together, we get 8. But by looking through the chart, we can tell there are only 7 possible outcomes that have either tails or a 6.
And that's where you can see the double count. So if you don't subtract that out, you would say 8, but it's not 8, it's actually 7.
We count tails and 6s independently. We double count the outcomes that have both. If we didn't subtract off the probabilities of tails and 6, we would double count it. Let's put these probabilities into a Venn diagram, and we can see even more clearly why we need to subtract P of tails and 6. If this circle is all the times we flip tails and the other circle is all the times we roll a 6, the overlapping area is counted twice if we simply added the 2 circles together. In this simple case, we could easily see what the probability of tails and 6 is, but sometimes it's not so easy to figure out. That's why we have the multiplication rule, which helps us figure out the probability of 2 or more things happening at the same time. Let's say you just found out that actor Cole Sprouse goes to your local IHOP pretty often, and there's a 20% chance he'll be there for dinner any given night. And yeah, I know that's not how people work, but we're going to say that that's how Cole Sprouse works. Anyway, to top that off, your local IHOP has a promotion where they randomly select certain nights to be free ice cream nights in the hopes that customers will keep coming back in case that night is the night. Each night there's a 10% chance that it will be free ice cream night. Now, you love ice cream and you like Cole Sprouse, as do we all, and your perfect night would include them both. So you try to calculate the probability that will happen on your visit tonight. Using the multiplication rule, multiply the probability that Cole Sprouse will be at the IHOP, 0.2, with the probability that it will be free ice cream night, 0.1, and you come to the sad realization there's only a 2% chance that you'll get to see Cole and get free dessert tonight. When we want to know the probability of 2 things happening at the same time, we first need to look at only the times when one thing, Cole Sprouse at IHOP, is true, which is 20% of the time. Now that we reduced our options to just Cole nights, out of all of those Cole times, how often is it free ice cream time? Only 10% of Cole nights. 10% of the original 20% leaves only a 2% chance that...
That's a good way of putting it. So you start with the 20% of one event happening. Of that 20%, 10% overlaps it. And so 10% of 20% is just 2%. So you're starting with one, multiplying by the other. And this is if you need both events to happen.
That both will happen at the same time. But you can always change your expectations and calculate the probability of getting either by using the addition rule, Cole or free ice cream, which is calculated by adding the probability of Cole to the probability of free ice cream minus the probability of both, so we don't double count anything. You realize there's a 28% chance that something good will happen tonight, so you decide to go. No matter what, you're going to get French toast. Cole Sprouse and...
Okay, that's good for that. So now I'd like you to go over to your text again on page 11 and run through these questions. We've got 3 questions on page 11, and I believe, is there one more on page 12? Yeah, one more on page 12. Pause the video for a bit and go back and work through those, and then come back to see whether you did them right. All right, so for number 1, so we're asking which of the following events are mutually exclusive. So that term was given in the video as cannot both happen at the same time. All right, so we want to know which one of these cannot happen at the same time. So picking a 4 and picking a 4 of clubs. Well, there is a 4 of clubs, so that would be picking a 4 at the same time, so it's not that. Picking any color of candy and picking a red candy. Well, if you pick any color, red could be the color, and then you've still picked a color, so it's not that. Rolling a 3 and rolling a 5, that's similar to the rolling a 1 and rolling a 5 before. That's the one that's mutually exclusive. Rolling a 2 and getting tails, those things could both happen, so that's not it either. So it should be C, rolling a 3 and rolling a 5. Those are the only things of this list they can't both happen. All right, consider the example from the video where you flip a coin and roll a six-sided die, which equation correctly represents the probability. So tails or six, again, since this is not a mutually exclusive situation, this does require us to subtract out the part where they both occur. And we're never going to subtract probabilities, so B is out. A would work if these were independent of each other, right? If these were mutually exclusive and they could not, I shouldn't have said independent, if they were mutually exclusive and they couldn't both happen. So that's not it. The one that we want to use is D because it takes the two probabilities of the events and subtracts out how often they both happen together. We're not going to add that on. That would more than double count it. So correct answer here is D. All right, number 3's got a diagram here, and it asks us the questions on the next page. So circle all the possible outcomes where you get tails. So hopefully you've done that. I'm going to circle them now. So my tails are here and here. And, well, actually, let me do it over this way. So tails, 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 tails. Okay. And then it also says to use a different color or shape, circle all the possible outcomes where you get an even number. All right. So the even numbers, I'll do those in this light blue. So that could be a 2, could be a 4, could be a 6, could be a 2, could be a 4, could be a 6. Okay. And define the following probabilities. Probability of getting a tail. Well, I did circle 6 different tails, right? And there were 12 outcomes total. So that would be 6 out of 12, which is 0.5 or 50%. Probability of getting an even number. Well, that was also 6 even numbers out of 12, so also 0.5 or 50%. Probability of getting a tail and an even number. Let's go back to that diagram for a minute and see. There were 3 times when I both circled and boxed a number. So that's 3 out of 12 that fit that description. So 3 out of 12. And that was also 50%. Whoops, 0.5 or 50%. Now the fraction version of this should have been reduced. I needed to do that back here. And this one's 1/4. The other way we can look at this AND version, if I need 2 events to both happen, we can take each of their probabilities and do 1/2 times another 1/2, and that gives us 1/4 that way too. So if we did not have a list drawn where we could easily consult the colors, we could do it that way as well. All right, what is the probability of getting tails or even? Let's go back one more time here. Tails or even. So we had 6 tails, we had 6 evens, but there were 3 times where we doubled those up. So I'm looking for anything with a marking, basically. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 different numbers that are marked. So 9 out of 12, which is 3/4, or 0.75. Okay, another way to do that would be to take the probability of tails plus the probability of even and subtract the probability of both. Okay, so probability of tail was 1/2, probability of even was 1/2, probability of both was 1/4, and if I just go left to right here, that comes out to 3/4. So the formula works. Okay, go back and review that if you need to. We're going to go on to the next section. It's addition rule section. So 120 ninth graders at Mountain Day High School. You all get to choose one of their 3 possible electives. So we can do choir, we can do computer science, or we can do student council. We have 72 choir, 27 computer science, 21 student council. All right, so pause here and go through this and write down the probability of each one. Okay, what you should have is 72 out of 120 for computer science. No, sorry, 27 out of 120, because 72 is choir, so 27 out of 120. And I think that reduces. I think we can reduce that by 3, so that would be 9/40ths in reduced form. If you use your calculator, that's 0.225, which is 22.5%. All those different ways of writing it. Okay, choir was 72 out of 120. And again, those will divide by 3. They might divide by more, though. I think they both divide by 12. Actually, we can maybe even divide by 24. Yeah, we're going to divide by 24 and get 3/5. And that comes out to 0.6 or 60%. And when you're reducing that fraction, you can reduce by whatever you want at first and then just keep on going until you get to its simplest form. So if you maybe did 2 or 3 or something like that at first, you can still keep going. Okay, computer science or choir, which means I need to take the probability of computer science plus the probability of choir. And it looks like they only get one elective here. So there's no possibility of both of these things happening. So I can just go with this addition and stop there. So I can do 9/40ths plus 3/5. Okay, and if I scale this up to 40ths, I would have times 8, so 24 plus 9 is 33/40ths. And that would equate to 0.825, which is 82.5%. And that checks out because I had 22.5 and 60, so the sum is 82.5%. So I did not need to subtract anything here because, once again, these were mutually exclusive. If you only get one selection, you can't possibly have both. Okay, so this is a theoretical version. This is not a context version. So we're going to do P of A or B. So that tells me I need to do P of A plus P of B and subtract P of A and B. Okay, so 0.43 plus 0.09 minus 0.02. And that comes out to 50%, or I mean 0.5, 50%. Okay, go to number 3, read the problem, see if you can get to the end without help. Pause the video here and try it. Okay, so we're looking at 48 total students, so that's going to be my denominator for any fraction I need to calculate here. Let's go through this. If you randomly choose one student, what is the probability they play video games or have a pet? Okay, so there are 30 who play video games. There are 36 who have a pet. So that's the probability of each individual event happening. Now I have to consider, is it possible that they have both? And this actually states it flat out. 27 of them have both. So I need to subtract those 27 who have both. Because if I don't, I will have double counted, and you can see this even comes out to more than 100% if I double count. So I need to make sure that I subtract those out. So 30 plus 36 would be 66, minus 27 would give me 39 out of 48 who do one or the other. And so that comes out to 0.8125 or 81.25%. Okay, so let's be in the habit of adding the fractions and then considering, could it be both? If yes, then subtract out the probability of both. If no, leave it as addition and stop there. All right, so page 13, and this is where we'll leave it for today. So we have a deck of cards splayed out here, all right, and that starts with an ace and goes to a king. This is called a jack, this is called a queen, this is called a king. For those that don't play cards, those three words are here. We have clubs that look like the little shamrocks. We have spades here that look like the little shovels, hearts, and diamonds. Those are the four suits. When you say suit, you're talking about the shape of the item on the card. All right, so if you look across here, there's 13 here, there's 13 here, 13 here, 13 here, total is 52. So anytime we're doing a cards problem, the denominator is going to be 52 if we're dealing with the whole deck. Okay. So, what is the probability that we pick either a king or a club? All right, so king or a club. Probability of a king or a club. All right, so there's that word or again. So what I need to do is do the probability of a king plus the probability of a club, and if there's a chance of both, subtract the probability of both happening. Okay. Well, what I know about this deck of cards is that there are 4 kings. There's 1 from each suit, so that would be 4 out of 52. The clubs, there are 13, right? So that's 13 out of 52. And getting a king and a club, there is 1 card in the deck that does that. Oh, that's the spade. Don't do that one. The king of clubs is right here. And that's just 1 card out of the whole deck of 52. So we just go straight across. Right? We do 4 over 52 plus 13 over 52 minus 1 over 52. And that's going to give me 4 plus 13 is 17 minus 1 is 16. Let's reduce this by 4. We're going to get 4/13. So there's a 4/13 chance of picking a king or a club in this deck. Right? And that's going to read, if we want to express this as a decimal, we can. It'll be approximately 0.308, which is approximately 30.8%. Okay, I think that's enough addition problems for today. So we'll leave that there. We'll do this other Desmos that's listed here next time. But for now, what you're going to do is go back to your laptop, back to your Google Classroom, and find the chance experiments. We're going to work on chance experiments.